Alright, in this video we're going to look at quadratic functions and determine the vertex, range, and intercepts of a quadratic function in standard form. So a quadratic function is a function in the form f of x equals ax squared plus bx plus c, where a, b, and c are real numbers and a is not equal to 0. You might remember some of this information from the quadratic formula. The domain of a quadratic function is all real numbers. In other words, you can input any number you want for x into a quadratic function and you'll get some output number in return. There are no restrictions at all for quadratic functions. So for f of x is x squared, this is the graph below. It's called a parabola. So here are some points on the graph. Notice that it's a mirror image for the left side of the parabola when you look at the right side as well. The y-axis is a line of symmetry. It's called the axis of symmetry because it splits it into two equal halves. So the point, in this case, the origin in this graph, the bottom of this parabola, the minimum point is called the vertex. And depending on which way the graph is opening, here we have a graph that's opening up, then the vertex is going to be a minimum. However, we can have graphs that open downward, which in that case the vertex is a maximum. So our vertex is a relative minimum if it's opening up, a relative maximum if it's opening down. We can graph parabolas using transformations to our parent function f of x is x squared. And that's what we're going to look at in this video. So example 1, graph the following functions starting with the graph of f of x is x squared, and then using transformations we're going to state those transformations and then find the vertex, state the range, and find the x and y intercepts if they exist. So we saw in the last video with complex numbers in the quadratic formula, if it doesn't, sometimes they don't hit the x-axis, which means the solutions are imaginary. But here's our function, g of x is x plus 2 in parentheses squared minus 3. So we have a plus 2 that we're adding inside the squaring function, and then we have a minus 3 that we're having outside the function. So plus 2 is going to shift our graph to the left 2 units, and then the minus 3 outside the function is going to shift everything down 3 units. Once again, here's the same graph. The vertex is at -2, -3, which notice that's the opposite for the x-coordinate of the vertex, -2. That's the opposite of what we have inside parentheses. The y-coordinate of the vertex is what's outside here, so what we are subtracting from the function. So to get the x-coordinate of your vertex, just take the opposite of what you have in parentheses next to the x. The range is y is greater than or equal to -3, so our lowest point on the graph is -3, and all the other y coordinates on the graph are higher than that. So greater than or equal to -3 is bracket -3, comma infinity, and remember, always a parenthesis after infinity. The x-intercepts, to find those, we just set our function equal to 0 and solve. So add 3 to both sides, we get x plus 2 in parentheses squared equals 3. Take the square root of both sides. Remember, when you take the square root of both sides, you got to consider the positive and the negative. So we have x plus 2 equals plus or minus the square root of 3. And so our x-intercepts, the exact values of them, are at -2 plus the square root of 3. So that would be this point right here. And then -2 minus the square root of 3 would be this point right here. So whatever those are, -2 plus or minus about 1.73, I think. So those are x-intercepts, -2 plus or minus the square root of 3, and then our y-coordinates are 0. All right. For our y-intercept, it's at 0, 1. So we can either get that directly from the graph, or if we plug 0 in for x, 0 plus 2 is 4, or 0 plus 2 is 2, 2 squared is 4, and 4 minus 3 gives us this y-intercept of 1. All right, part B, we have h of x is -2 times the expression x minus 3 in parentheses squared, and then plus 1. So here's our graph of h of x, and let's see. Well, first we have this negative out in front of the function. That's a reflection across the x-axis. The 2 that we're multiplying the function by is a vertical stretch by a factor of 2. x minus 3 in parentheses. The minus 3 means we shifted to the right 3 units, and then the plus 1 means we shifted up 1 unit. So our vertex, we started at the origin, we flipped it up across the x-axis, stretched it vertically by a factor of 2, and then moved everything 3 units right and 1 unit up. And that's our vertex at 3, 1. So the opposite of negative 3 is 3, and then we keep the 1 as a 1. So it's just, the vertex is just the transformation for the horizontal and vertical shifts of our original vertex, which was at the origin. This time our y values are less than or equal to 1. So less than or equal to 1, parenthesis negative infinity, comma 1 with a bracket afterwards. So every y coordinate on this graph is 1 or lower. Our x-intercepts, we're going to set this equal to 0 and solve. So first up, let's subtract 1 from both sides. We get negative 2 times x minus 3 and parentheses squared equals negative 1. Then divide both sides by negative 2. We get x minus 3 and parentheses squared equals a half. Take the square root of both sides. We get x minus 3 is plus or minus the square root of a half, which, if we break that down, is plus or minus the square root of 1, which is 1, over the square root of 2. And then if we rationalize 1 over the square root of 2 by multiplying the numerator and denominator by the square root of 2, we get plus or minus the square root of 2 over 2. And then add 3 to both sides, and we get our x-intercepts at 3 plus the square root of 2 over 2, so that's this point here, and then 3 minus the square root of 2, that's this point right over on the left. Our y-intercept, we'd have to scroll down a bit to see it on the graph, or we could just plug a 0 in for x. 0 minus 3 is negative 3. When we square that, we get positive 9. Negative 2 times positive 9 is negative 18, and negative 18 plus 1 is negative 17. So if you graph this, and you have to probably scroll down or zoom out to finally see where it hits the y-axis. All right, that about does it for this video. Thanks for watching, and I'll see you next time.